So we've talked about addition and subtraction with our algebraic numbers. It's now time to take the next step, look at multiplying the algebraic numbers. We hinted at this a little bit in the last class as well, where we had things like 3x times 7x. And you'll recall that the difference between addition and multiplication is, in multiplication, we don't need to have the same names, because in multiplication, we're going to also multiply the names. So here, 3x times 7x, we do 3 times 7 to get 21, but we're also going to multiply x times x to get x squared. So where we couldn't add something like 5x squared and 3x, because they're different names, x squared and x are different, we can multiply them. Because when we multiply, we do not need the same name. We're going to combine the counts. 5 times 3 is 15. And also combine the names. X squared times x is x to the third. We can have digits with multiple names. We can have something like 4xy. And I might multiply that by something like 6x squared. And when we do that, just like always, we combine the counts. 4 times 6 is 24. Now to combine the names, xy times x squared, we have to do a little bit of moving around. Just like we did kind of with those negatives, we took 5 times negative 3 and we turned it into negative 3 times 5. We can move this around as well. We can take the x and the x squared and combine them together to get x to the third, x cubed, and then the y doesn't change. So if we have 7x squared y to the fifth times 2x to the third y, we can combine the counts. 7 times 2 is 14. Then we can combine each of the names separately. Basically what we're doing is just doing x squared times x to the third is going to be x to the fifth. Good. Because we have 2 x's. X squared is 2 x's. X to the third is 3 x's. That is now 5 x's multiplied together, or x to the fifth. And then y to the fifth times y is y to the sixth. Good. Again, we have 5 y's multiplied together times another y makes 6 y's multiplied together, or y to the sixth. Well, let's take this a step further. What if we had something like this? Well, again, we see that parentheses, and as always, it should scream at us, do something here first. But when we look inside that parentheses, there's nothing we can do. 5x and 2 cannot be combined because they have different names. In fact, like we said before, that is really a single number. 5 x's and 2 1's. But the parentheses still has to be acknowledged. And if there's nothing that we can do inside the parentheses, we have to look and see if there's anything that needs to be done to the parentheses. And here there is. The parentheses is being multiplied by the 3x. How do we do that multiplication since it's more than one digit here? Well, this is exactly like we would have done 24 times 3. You would do 3 times 4, then you do the 3 times 2. Same thing's going to happen here. We do the 5x plus 2 times 3. Well, what's 3 times positive 2? positive 6. What's 3 times 5x? Well, 3 times 5 is 15x. Oops, I missed something there though, didn't I? That's a 3x, isn't it? Sorry about that. Let me back up now and redo this. Now that with a 3x times 2 will be positive 6x. 3x times 5x will be 3 times 5 is 15. X times x is x squared, or x to the second. So the operation is really the same as multiplying whole numbers. It just looks different because we have the variables in there. Now, many of you were probably taught something called distributing. Look like this. Do 3x times 5x is 15x squared. 3x times 2 is positive 6x. That's fine. It works. It's just a shortcut is all it is. It's a shorter way of doing this. Most of us were never shown the real way of doing it. We were just shown the shortcut. At a certain point, I'll switch over and I'll start doing them this way myself. But for now, we're going to do I will do most of them the long way. When you do them in your homework, do them however you're comfortable with, of course. So yes.
What exactly does the word squared mean?
The word squared, good question. Squared just means to the power of 2. So if I say x squared, that's really just x to the power of 2. That's just kind of the slang term. Okay, let's take a look at this. So here again, we're just going to write this out. 7x negative 3 times a negative 4x squared. So now we just do the negative 4x squared times negative 3. What's negative 4 times negative 3? Careful. A negative times a negative will be positive, and 4 times 3 is 12. Now the x squared doesn't, the x to the second power doesn't multiply anything, so it's just x to the second power, x squared. Now we have the negative 4x squared times 7x. Negative 4 times 7 is negative 28. X to the third power. Good. X times x squared is x to the third. I'll do the next one right beside it here. So here, this is a little bit longer, but it's going to follow the exact same process. 8x squared, negative 5x, positive 2, times 5. So the 5 times positive 2 is positive 10, good. 5 times negative 5x, negative 25x, good. And 5 times 8x squared. Perfect. 8 times 5 is positive 40, and it's just x squared. Now you might be thinking, what name is this here? Remember, that's the ones. So ones times anything just stays the same. So this stays x, this stays x squared when we multiply the names. We can combine a little bit with that. We could have something like this. This is really just an order of operations problem. What I just put here is absolutely no different than this. Over here, what would I have to do first? Multiply and then subtract, right? Over here, what do I have to do first? Multiply. Yeah, I mean, I see the parentheses and it draws me to them saying do something here first, but there's nothing in there I can do. So the second question is always, is there anything that I have to do to that set of parentheses? And there is. I have to multiply by the 8x. So this is 3x plus 7 times 8x. So now 8x times 7 is 56x. 8x times 3x, 24x to the power of 2, or x squared. Now I can't forget, I still have a subtracting 8 over here. But looking at these, can I subtract 8 from any of these digits that are here right now? No. So I end up just putting the minus 8 on the end. Technically what I'm doing is this. The negative 8 would go over here, and I'd put a plus 0 ones on the end. 0 minus 8 is a negative 8. And it looks like that. Make sense? Oh, what if instead of having a minus 8 on the end, I had something with a variable on it? What if I had this? Something like that. What do I have to do first? Anything in parentheses to do? Nope. So I have to do to the parentheses, which is the multiplication. So I do have to do the 7x to the third minus 5x times the 2x squared. We do always have to double check to make sure there isn't anything in that parentheses that we can do before we move on. So now we have the 2x squared times negative 5x, which is negative 10x to the third power. Good. The 2x squared times 7x to the third. Careful. 2 times 7 is 14. X to the fifth. 2 plus 3 makes 5. Now we still have this plus 6x to the fifth here. Where do I add that? Perfect. I can add that to the 14x to the fifth, which makes 20x to the fifth. And I still have the negative 10x to the third. This one here is a little bit trickier. There are two ways we could think about this. We could think about this as being, of course, we have to multiply these two together, and we have to multiply those two together, and then subtract. But when we deal with algebraic numbers, subtracting isn't very easy to do, is it? It gets confusing. So the easier way to think about this, and the way I'm going to do it, is this. We multiply these two together like we said. Then we multiply these two together, treating that as a negative 4 times all that. The reason I can do that is, remember, when we subtract, we can change it to plus the opposite. So instead of minus 4, we're going to think of that as plus a negative 4. So now, again, we double check. Is there anything I can do inside the parentheses here? Nope. How about here? Nothing there either. So now I go back. Is there anything that can be done to this set of parentheses? You bet. It's multiplied by the 3x. So 5x minus 2 times 3x. 3x times negative 2. Perfect. Negative 6x. 3x times 5x. Oops, careful. Positive 15 x squared. Yep.
Yeah.
3 times 5 is 15.
I said 6.
Yeah, that's okay. Now over here we got the same thing. 7x squared minus 3, but I'm going to multiply not by 4, but by negative 4. So now negative 4 times negative 3 is positive 12. Negative 4 times 7x squared. Perfect. Negative 28 x squared. So right now, this is what I have, but I'm not done yet. What can I still do? Yeah, I have two digits that have the same name, don't I?
Right.
Yeah, I have the 15x squared and I have a negative 28x squared that can be combined. What is 15 plus a negative 28? Well, 15 looks like that, positive 15. Negative 28 goes the other direction. Is it longer or shorter? It's longer. So we're going to be in the negative side of things. By how much? Well, 28 minus 15 is 13. It's a negative 13. We keep the same name. It's still x squared. We still have the negative 6x there, and we still have the positive 12. So those do get to be a little confusing. Let's do one more example of that just to be sure we have it. Okay, here, tell me what to do. Okay, perfect. So we got the 3x cubed plus 9 times 5, which gives us 5 times 9 is 45x. 5 times the 3x cubed is perfect. I'm done there. Now I move over here. This is 6x minus 2. Is it times 3x squared or is it times the negative 3x squared? Why would I even ask that? It's a positive 3x squared. Up here, this became a negative 4 because it was minus 4. Down here, it's almost silly of me to ask because there's no negatives here anywhere. It's a plus 3x squared. There's no reason to even worry about it. But I wanted to make sure you understood where that negative came from before. So we go ahead and we multiply. 3x squared times negative 2. Negative 6x squared. Good. 3x squared times 6x. 18x cubed, or x to the third. And it's a positive, so I'm going to put a plus there. Are we done? No. We can combine 15 and the 18x cubes to get 33x cubed, or 33x to the third. Now, technically, which one should go next? It should go in descending order, so it should be negative 6x squared, and then the positive 45x. Descending order means largest power to smallest power. So 3, 2, 1.
Oh, when the power is first.
Yeah. So that's why the x squared, we moved that up here because it's a bigger power than just the x.
Okay, yeah.
Now that's just a grammar issue. If you were to write this answer as 33x to the third plus 45x minus 6x squared, there's absolutely nothing wrong with that. It's just one of those kind of grammar things where we prefer to see it in that form. Okay, Now we could take the next step, and I'm just going to show you this really quickly. We're not going to do a lot of it now. We'll come back to it more later and do more. But what if we had two-digit numbers like this? 2x plus 5 times 5x minus 3. Again, this is absolutely no different than whole number long multiplication. 2x plus 5, 5x minus 3. We start with this last digit of the bottom number. What's negative 3 times 5?
We're plus or minus?
We're multiplying here, sorry. Multiplying. Negative 15, good. What's negative 3 times 2x? Careful. Negative 3 times 2 is negative 6. That's just going to stay x. So now we've done everything we can with the negative 3. What do we have to make sure we do down here before we move over? Well, we put in a space here, or put a plus a 0 in that spot, so we move over a spot. Now we can do the 5x. Now 5x times 5, 25x. It's positive, so we put a plus 25x. And 5x times 2x, 10x squared. Good. You can see this works out just like long multiplication did. So now we've got the negative 15 and 0 is negative 15. Negative 6x and positive 25 is a positive 19x. You have negative 6 and positive 25 would look like that. On the positive side, the difference between 25 and 6 is 19. And then nothing changes the 10x squared. Now there's a process we will come back and see more of later. But I wanted to introduce it to you now just so you can see how the algebraic numbers really do follow exactly the same rules as our whole numbers. It's not some new set of procedures that we need to memorize. It's the same two basic processes. Now, the next thing I want to go over is what I believe to be quite possibly the single most difficult task in math. That is taking words and turning them into symbols or equations. If I were to tell you something like, if you hear the phrase, 8 more than a number, what would that make you think? Well, you might, there you go, 8 plus a number or a number plus 8. More than usually indicates addition. So you can pick a variable to represent a number. Usually we go with x or n or y, but you can use any letter you want to as that variable. I'm going to go p plus 8 or 8 plus p. With addition, it doesn't matter what order we put them in because addition is what we call commutative. That's a really big word to describe a simple process of if 3 plus 4 equals 4 plus 3. It doesn't matter what order you add the two numbers in. But what are some other phrases that might imply addition? Well, of course, plus. 8 plus a number would be 8 plus p or p plus 8. Added to. 8 added to a number. Increased by. A number increased by 8 would be p plus 8 or x plus 8 or whatever. One that a lot of people have forgotten is sum. The sum of a number and 8 is x plus 8 or 8 plus x. And of course there are others out there, but those are the ones you'll see most often. This one is just a little bit tricky. When you look at that 5 less than a number, most of us would right away go to the operation of subtraction. But you might be tempted to do 5 minus x. And that's not true. There you go. It's 5 less than the number. So it's the number minus 5. It's the 5 that's being taken away because it's 5 less. Now you'd have to be careful. You take out one word there and it's significantly different. Instead of 5 less than a number, 5 less a number is way different. That is 5 minus x, or 5 minus whatever variable. So when we're subtracting, the order does matter. Subtraction is not commutative. So other phrases that indicate subtraction, you might have decreased by. Along with decreased by, you might have reduced by. Subtract, a number subtract 5. And kind of like sum, we have the word difference. The difference of a number and 5 would be x minus 5. The difference of 5 and a number would be 5 minus x. Whatever order they're stated in is the order they're subtracted in when you use the phrase difference, the term difference. And of course, eight times a number, that one's pretty easy. 8 times n or 8 times x. Now I put times in here, but I don't have to. I could just write 8n or 8x, which means 8 times whatever that letter is. There are other phrases, of course. You could put multiplied by. And of course, like the sum and the difference, we have the product. If I say the product of five and a number, does it matter whether I put 5x or x times 5? No, it doesn't. Both of those mean the same thing. Once again, multiplication is commutative. It doesn't matter what order we multiply two numbers. 2 times 5 is the same as 5 times 2. Now when we switch to division, however, it does change up. We might have a phrase like a number split 3 ways. Well, that's going to be x divided by 3. And I can either write it that way, x or n or whatever letter I want to use, divided by 3, or I could do x over 3 means the same thing. If you recall from yesterday, we said that fraction bar can also be used as division. Other phrases, of course, for division, we could do divided by. And like the sum and difference and product, we have quotient. Good. The real tricky part comes when we start combining more than one operation into these phrases. We might have 6 times a number increased by 5. Perfect. 6n plus 5, or 6x plus 5, whatever letter we want to use. It is 6 times the number, 6n, then increased by 5 is plus 5. This is very different from the phrase six times the sum of a number and 5. Now, when we first look at that, it looks the same. Sum means addition, and it's times 6. But the difference is here, it was 6 times the number. So it was 6 times n. Here, it's not 6 times the number, it's 6 times the sum. The sum is the result of an addition problem. What that's telling us is that we had to add first. So the sum of a number and 5 is x plus 5 or n plus 5. And then we are multiplying it by 6. So we have to have the parentheses in there telling us we found the sum first. Then we multiplied by 6. Very similar to that, we could have 2 times the quotient, or sorry, not quotient, the difference of a number and 7. Same thing. 2 times the quotient, or the difference, means we found the difference first. We subtracted first. So the difference of a number and 7, since it's a number and then 7, means it's n minus 7 or x minus 7. And then 2 times that difference means we put it in parentheses. It's 2 times. Any questions? Now, as we start doing more and more word problems as the semester goes on, I know I said the W thing, word problems. They will get easier for you as we go on, by the way. This is one of the processes we're going to have to practice. And if you're looking at one of these word problems and you cannot see where I get this equation from, let me know. I'll be happy to go back and try to go through it a different way so you can see it. Because like I said, that is possibly the most difficult skill in math, is picking out from words some sort of mathematical symbols that we can calculate with. Story problems, yes. I know we all hated them when we were younger. But let's face it, life is a story problem. Nobody's going to walk, your boss will never walk up to you and say, hey, what is the sum of a number and 8? They're going to say, well, last month you sold this many and we need you to increase that by, life is a story problem. Hang in there. We'll keep going over them as we need to as well. I'm not going to just throw you into the pit all at once. Some of the other things we can do with these variables. We can have an expression. Let's say that we know our annual sales generally take the form of P plus 2m squared minus 7. Where P is a base sales number, M is the foot traffic, the number of people that walk past our business on a given day. So let's say we know P to be, I'm just going to put some small numbers in here to make it easier for us to work with. Let's say we know that P is 8, and during a certain period of time, M is 3. What is the value of this going to be? Well, now these letters, the P and the M, are no longer variables. We know what they are now. We have numbers for them. So we can rewrite this, replacing those with their values. Instead of P, we'll write 8 plus 2. Instead of M, we'll write 3. So instead of M squared, it is 3 squared. Now we have to remember this 2m squared is really 2 times m squared. So this is 2 times 3 squared. and we have the minus 7. Now from there, what would we have to do next? The 3 squared. We do the power. 3 squared is 9. Next, we'd have to do the multiplication. 2 times 9 is 18. And we have nothing left but addition and subtraction. So 8 plus 18 is 26. Minus 7 is 19. We can express them in a little bit different way. We might have something like this, where y equals t plus 2 times 16 minus m. And we might be told that t equals 12, n equals 5, and be told to find y. Well, again, this really doesn't change the problem at all. It just looks different. This part up front here really means nothing at this point. We're asked to find y, and y equals this. So what we're working with is this green box. And we have all the values to replace the variables on that side of the equal sign. So t is going to be the 12 plus 2 times the parentheses, 16 minus 5, and we close the parentheses. So all we have to do is do our order of operations. We have to do the enclosing symbols or the parentheses first. That's going to be 11. We don't need the parentheses anymore. We remember to put in the multiplication between the 2 and the 11. 2 times 11 is 22. 12 plus the 22 is 34. So what this is all telling us is that y equals 34. That's what we call evaluating an expression. Anytime we have an algebraic number like this here, where we have the variables and numbers mixed together, we can evaluate it or get a numerical value for it if we know or if we're told the values for each of the variables in that expression. So it really is nothing more than order of operations at that point. Now the next thing we can use these variables for, and the last thing we're going to go over today, is something like this. X equals 8. Solving an equation. This is an important enough concept that I'm going to end this recording here, and I'm going to make its own recording here in just a second. So let me